Or you want to maybe start?
Yes, I mean, now I present you to everybody. Today with us we have Eleonora. Eleonora is a PhD student at the Simula Research Laboratory at Oslo, and today she will talk about parameter robust preconditioning by congruence for multiple network poroelasticity. Thank you, Eleonora.
Thank you. Thank you for inviting me. Thank you, Matteo, for inviting me, and thank you, Maria, for helping me with all the bureaucratic stuff for this talk. So this is a work that now it's actually in a paper. It's available in the archive if you're interested in reading it. It has also been submitted and it has been gone through a first round of review and hopefully last. So hopefully it will be published soon. It's a joint work with my main supervisors that are Kent André Mardal and Marie Elisabeth Rognes, and two other scientists, John Lee and Travis Thompson. So in this talk, we will mostly look into these equations that are called the multiple network elasticity theory equations. This is a system of equations that describes the behavior of a network of a fluid in a solid. So it is poroelastic solid. And the assumptions that we make here is, well, there are several. Let's say the main is that we assume that the solid can be modeled as a linear elastic solid. So with the classic Lamé constants mu and lambda positive. And that so this is the first equation, and it is a vectorial equation, the momentum equation. Here we have the stress tensor coming from the solid and here coming from the fluid. And for each network in the fluid, in the solid, each fluid network, J, we can write a continuity equation. So as you can see, there are a lot of parameters. Now I'll try to mention all of them so that it's clear what we're talking about. So this mu and lambda, as I said before, are the Lamé constants. Alpha J for each network, it's what is called a BO Willis constant, and it is smaller than 1 and positive. This Sj, it's what is called a storage coefficient. Kj is the hydraulic conductivity. It can be a tensor. In our case, we consider it to be a scalar, and we consider it to be uniform in our domain. And this is, I mean, maybe the interesting part, I don't know, definitely numerically it is. This describes the exchange of mass between the networks. And basically what we're saying with this expression is that the exchange between the different networks is dominated, is regulated by the gradient. So the difference of pressure between the network J and the network I, multiplied by an exchange coefficient xji. On the right hand side, we have pretty standard things. We have some external forces, volumetric forces F, and for the continuity equation, this Gj for each network J, it can be seen as a sink or a source. So if we are injecting or losing fluid. So these equations have been used in multiple applications. So for example, in the brain tissue, so one can see the brain parenchyma as a fluid, as a solid that is permeated by several fluid, like the extracellular fluid, the blood that can be found in the arteries, in the veins, and the capillaries, or as it was initially intended to model poroelastic rocks. So indeed, these equations can be seen as an extension of the one network equations, that there would be the more famous bio equations. So for simplicity and to explain some concept that I will show later, we can start looking at a subset of this equation. So if we forget for a moment of the solid part, we can consider just a network of fluids. And in this case, we only have the hydraulic conductivity, Kj, and the exchange terms. So this system can look quite simple. It's just a diffusion here, and here we have some mass matrices. But the challenge is mostly due by the fact that these parameters can change heavily, both the order of magnitude of Kj with respect to these exchange coefficients, but also the parameter itself for different applications. So here in this table, there are some parameters that I found in the literature to give just an idea of how big the difference between the order of magnitude and also within the parameter itself can be. Okay, so if we look at the, so as I said here, so we have this, this is just a Laplacian for basically a diffusion term for the pressure with this hydraulic conductivity coefficient, and here we have this exchange coefficients. So if we want to write this in an operator form, we'll see that the matrix K that contains the all the hydraulic conductivity coefficients, is a diagonal matrix, and it is a positive matrix if these K's are positive, and they are. We assume that. And this instead is it's not it's real and it's a symmetric matrix, but it's it is weakly row diagonally dominant by definition. Also, what is interesting is that the sum of these elements is 0, row-wise and also column-wise. And so this is not a strictly positive matrix. So we can write our system in such a way, operator-wise. And now our question was, we have these operators, we want to find an efficient preconditioner. How can we do it? So this matrix here is nice, is symmetric, is diagonal, so we could just take the diagonal blocks. But this one, it's not diagonal. We have all these extra diagonal blocks. So if we want a block diagonal preconditioner, what we can do, our idea was to basically do a change of variable. So the question is, how can we diagonalize both matrices together? And this, here comes the concept of diagonalization by congruence. Basically, we can assume, as it's exactly in the case that I just showed, that we have two matrices, K and E, that are both symmetric, where only K is invertible. And as I mentioned before, E is actually a singular matrix by construction. And then we get these operators here, where this, with this notation, we mean, so we have a K Kronecker product or outer product with A, and this T is E Kronecker product with B. So in our case, A is the Laplacian operator, and B is nothing else than the identity matrix. So when we're going to write our system in a weak formulation, we would obtain something like this. Nothing strange. But then our question, then this theory that you can find in this book, Worm and Johnson, 1990, tells us that because of how these matrices are built, K and E, where K is invertible, we can find a transformation matrix P that transforms our system in such a way where we have p tilde instead of the p, and our operators from S to T, they become ds and dt, where ds is a p transpose kp, Kronecker product A, and dt is p transpose ep, Kronecker product B. And this p transpose kp and p transpose ep are diagonal. So now I show, I have to, let's see. Perfect. So this. Now I would like to show you, so we were here, and now I would like to show you a practical example. So let's assume that we have a two-network system. How can we practically diagonalize at the same time the matrices K and E by congruence? So if you have two networks, we're going to have two hydraulic conductivity, K1 and Ke2. And this is, as we said, a positive symmetric diagonal matrix, therefore invertible. The matrix E, this, as we said before, physically it describes the exchange between different networks. So we have, and also it's a symmetric. And as I said before, if we sum the elements row-wise or column-wise, we obtain 0. So it's a singular matrix, but it is symmetric. So the trick to obtain this transformation matrix is basically to compute another matrix C, that is K to the minus 1E, and this is what we get. And then the transformation matrix is composed, the column of this transformation matrix is composed by the eigenvectors of C, that in this specific case, they look like this. And then we do what we saw previously in the previous slide. So we obtain a K tilde that is just T transpose KT, and it is diagonal. So it is different from before, but it's still diagonal. So we didn't ruin what we like from this matrix here, that it was diagonal. And now we have an E tilde that is T transpose ET. So we get something like this. As you see, we have zeros here because this is not positive, strictly positive matrix. So this is a practical example. In general, what we obtain, if we could do this for nj net, for several networks, so if we had, for example, J networks, we would obtain, we can obtain a system that is basically diagonal, and this kj tilde are the diagonal entries. In the case 2 by 2, it would be k1 tilde will be k1 plus k2, and this will be k2 tilde, and c tilde, here they will be the diagonal elements of this E tilde matrix. So this is the norm that we can define for this transform system. And therefore, this is the preconditioner that we can use. And now it is quite straightforward to see that basically the operator A of the transform system, A tilde MPET, and the operator B, that is the preconditioner of the MPET tilde, they are spectrally equivalent, and therefore this is a robust preconditioner. So now what can we do for the initial system, the system we started with, that was the MPET equations? If you remember from the first slide I showed you, these MPET equations, we only had two equations, one vectorial equation that was describing the forces, the momentum equation, and then we had the J continuity equation. So here we use a little more complicated formulation actually, It's what we call the total pressure formulation. It's not much different in principle to what one would do when you have just the linear elasticity equation and the Lamé constant lambda goes to infinity, is to introduce a new equation for that part. So here what we do is that we introduce this total pressure P0 like this, and therefore the system is written in such a manner. So if you remember, in the continuity equation we had the term divergence of u that now has been substituted by this lambda P0 over lambda plus 1 over lambda summation of alpha j Pj. So we use this notation here as it's written here, where alpha dot p is equal to the summation of alpha I pi. Again, if we look at this in its variational formulation, we obtain something like this. And this is already in the time discrete version. We use implicit Euler to discretize time-wise. So here we have this form here, AUV. This is just the elasticity part. And then we have this BV Q0 here, and that we find here too. And then we have all these different terms that are related to the pressure. So these are several, so I'll try to go through them. So here we have this mass matrix for the total pressure that is here. And then we have this mixed term between the total pressure and the fluid pressures, that it is here, that is the C2. And it's weighted by the coefficient alpha, that are the Biot-Willis, and the lambda, that is the Lamé constant. And then we have this part here. So this part here, if we look carefully, it is very similar to what we saw before for the simplified system. So we have this diffusion term here, Laplacian, and then we have this exchange term here. And then in addition to this, we have this storage term here. And we have this other term here that comes from the coupling with the displacement. As I said before, we had a divergence of u in the continuity equation that now has been substituted with the P0 and P, because we use this total pressure formulation. So altogether, these terms C, P0P, Q0Q can be summed all together, and we can obtain something like this. So maybe in a more compact form, we get something like this. So this is a saddle point problem, and one could use saddle point theory to try and find a preconditioner. But this is not straightforward. It's quite involved, and especially because the parameters that we have are so many, and they can vary very much. So here we have an example of what, for example, of what a naive preconditioner could look like. So this is pretty standard preconditioning for this part here. Here we can use the identity or mass matrix. That's what we're talking. Yeah, this is like a bit of abuse of notation. And in this last block here, we can take the diagonal of this block here, C3. So the diagonal terms is, we have this Laplacian term here, we have this mass matrix here, we have another mass matrix here, and another mass matrix here. So basically we have Laplacian that has been weighted by the Kj, and here we have basically 1, 2, 3 different mass matrices that are weighted with different coefficients. So this, sorry again. I have to stop clicking on it. So it would be really nice if such a naive preconditioner would work with all the parameters. Of course, before trying more difficult things, we tried this naive preconditioner, but unfortunately it doesn't work. So here I present some numerical results. We tested our preconditioner on a square matrix, a 1 by 1 square matrix, where the square domain has been divided into n by n squares, and so where n here goes, sorry, the mesh is a triangular mesh, and that has n by n elements per each side, and n goes from 16 to 128. We consider a two network system where the exchange coefficient is 10 to the power of 6, and then we keep all the other parameters kind of fixed. So we take tau, that was the time step, equal to 1, the Lamé constant mu equal to 1, the exchange coefficients, sorry, the storage coefficients S1 and S2 equal to 1, and we take the BO coefficient equal to 0.5, and the K1, the storage coefficient, the hydraulic conductivity for the first network to 1. So we vary the hydraulic conductivity K2 for the second network, and we also vary the lambda parameter, so the Lamé constant. Remember that I said before that we use the total pressure formulation because it is robust with respect to the parameter lambda, in the sense that when lambda goes to infinity and the solid becomes incompressible, this formulation is robust. We don't see locking issues, for example. So we can see that when the ratio between the exchange parameter and the conductivity parameter is very small, these iterations keep growing with the size of the mesh. So it is not robust with size of the mesh, but we see that it does not increase with lambda. So we start, it stays contained within lambda. So this is kind of a proof that, or like a sanity check, that our robust formulation is at least okay for that. But this preconditioner is definitely not robust with respect to these parameters. So what is the strategy that we are going to apply now? It's kind of similar to what we did before for the simplified MPET equations, where we only had the fluid part. So what we do, we're going to look at these operators. So we have this C2 operator. Maybe I can go before so you can remember. So we have here, this C2 are in this operator. So they couple the total pressure and the fluid pressures. And here C3 is the fluid pressures operator. Okay, so the operator C2 looks like this, and the operator C3 instead looks like this. So we have, as I said before, this K Kronecker product with the Laplacian delta, and then we have all these coefficients. So the storage coefficient, the exchange coefficient matrix, and then this L coefficient, that is this lambda to the power of -1 alpha I alpha j matrix. This is what the entries of this matrix look like. Then multiply the identity matrix. So if you remember how I can go back and show you again how it looked here. How it looked in our case before. We had the kind of the same. We had this Laplacian operator, Kronecker with the hydraulic conductivity, and we had the exchange coefficients, Kronecker with the identity matrix. So now that block looks a little bit more complicated, but it is indeed very similar. So we have again this. Now we have also the time step that multiplies k, because we had a time-dependent problem that we have discretized. But this is the first part, so very similar to what we had before. And here we also have a bunch of matrices that are positive. So this is a positive matrix and diagonal. This is a positive matrix, and this is not a semi-definite matrix by construction. That they do Kronecker product with the identity matrix. So we can do the same. We can find what we did before. Let's find a transformation matrix P that simultaneously diagonalizes the matrix K and the matrix tau E plus L. So this can look a little puzzling because one would think that we should consider all of this, but the storage coefficients Sj are not involved in the simultaneous diagonalization process in order for us to achieve a parameter robust preconditioner that is robust also when the storage coefficients vanish, so when they go to 0. So after we apply this transformation, what we get is something like this. So notice that we haven't touched the operator A, that is the one regarding the displacement. This B transpose B haven't been touched. This operator also hasn't been touched. The only part that has been touched is the one related to the fluid pressures. So the displacement U and the total pressure P have not been changed, but the fluid pressure P, they pass from P to P tilde. And this is the way this transformation is applied. Similarly to what we do before, and also maybe I should, because we have a new symbol here. So basically the new matrix K tilde is now diagonal of K1, Kj tilde. And instead the new matrix here, we call it gamma tilde. On its diagonal, it has these new values that we call the gamma tilde. So gamma tilde is the diagonal elements of this new matrix here. Here we go. So as done before, we can define a norm now based on these considerations. So it is a norm that looks like this. And when we have this pedix here, it means it's a weighted norm by 2 mu and 1 over 2 mu. And then here we have our tau Kj tilde and the gamma tilde. And this is now the preconditioner we came to, that we found. So now we can use this new preconditioner to the transform system. And here we have some results. So this is a dense image. I'll try to explain a bit better. So on the x-axis of this image here, we have the value of K2. So K2 goes to 10 to the minus 6 to 10 to the minus 10 to the 0, so to 1. On the y-axis, we have instead the exchange parameter xi 1 to 2. So here it is again the same setup as we saw before with the results in the table. So it is a uni-square mesh, and it's a 2D uni-square mesh. And then so if we take, for example, this little square here, it means that we're looking at the case where the exchange parameter is equal to 1 and the hydraulic conductivity 2 is equal to 10 to the minus 6. And then each of this vertical line is represents the value of how fine the mesh is. So for the first vertical line, we have n equal to 8. Here we have n equal to 16. Here we have n equal to 32. And then here we have n equal to 64. Now, in each of this square, for each of this block, we have several lines. And each line has been, for each line represent a simulation that has been done at different mesh resolution. And you can see here that the triangle, they indicate for which value of the Lamé parameter lambda. So these triangles here, with pointing up, it's lambda equal 1. This triangle pointing down is lambda 10 to the 2, and this is 10 to the 4, and this is 10 to the 6. So if we take another square, for example, this square here, we are, and this line here. So this point, it is at the exchange coefficient 10 to the 4, hydraulic conductivity to 10 to the minus 2, mesh resolution n equal 8, and lambda equal 1. And the color of these triangles here, it's the number of iteration of our mean rest solver for the preconditioner that we used. So we can see that compared to what we obtained before, I can even, where we were seeing that when the ratio between the hydraulic conductivity, K2, and exchange parameter, XC12, was very small. So we would be in this case, for example, here. The number of iterations were exploding before, but now they are very moderate. So we are around 30, yes. And they are bounded. They don't, the maximum is around here, 70 for these values. So to summarize, we have shown a way to transform the variables in a system such that the system is more easily preconditionable with a block diagonal preconditioner. And we've shown that this approach gives quite nice results in the sense that we managed to obtain a preconditioner that is robust with respect to the material parameters and also the mesh parameter. And now I'm happy to answer some of your questions, and I would like to thank you again.
Thank you, Eleonora. So guys, it's question time. If you have questions, you can unmute yourself.
I have to, one moment. Yes, let me stop sharing my screen maybe.
I don't know. Actually, I mean, I have some questions for you,
yes,
Eleonora.
But
so.
Let me see if I can. I think my Zoom is a bit
frozen.
I don't see anybody. 1 second.
I mean, it's not a problem. Can you hear me first of all?
Yes.
Okay. Maybe I can stop your sharing and you can share again. Okay. Okay.
Oh, nice.
Okay. I have some curiosities actually. In the sense, first of all, I was questioning myself about how large is usually the system. I mean, how many points in the networks usually you consider for I don't know, several physical applications from the brain to the porous media?
It depends. Just stop my sharing again so that so I can see you better for me.
Okay.
It's just so weird.
No worries, fine.
Yeah, it can be a really big system if we consider. So in this paper is pretty numerical. So we of course presented some numerical examples, but it's like on unit squares. We also did some unit cube experiments, what is called the footing problem. That is a very common problem. But if we do numerical, like real applications, in this case, in my group, we are very interested in brain modeling. So we have a brain mesh, and that can be a million of cells.
Okay.
Then usually, so these MPET equations for the brain, usually you consider 4 fluids. You can consider what is called an extracellular fluid, and then you have 3 networks for the blood, that is arterial, the capillary, and the venous. So in our case, we used P2, P1 elements, so the lower Taylor roots elements. So you would have P2 elements for the displacement, and then you would have a P0, that is the total pressure, and 4 more fluid pressure. So it would be really...
Okay, yes, it's a mess.
It can be intense, yeah.
Okay, and okay, so now I was thinking about the saddle point structure of yours.
Yeah.
I mean, of the system, and you said that basically with the naive procedure, for some parameters, the iteration exploded. Yeah. Can you explain to me what they, the parameter, what they represent, in the sense the naive procedure works fine for some physical features, but not for others.
Yes, exactly. So let's see if I can share again, and then let's try if I can. This is like, let's see, maybe.
I mean, I would like to understand. This is actually the the table. Yes.
Yeah. So this
I would like to understand what is the physical setting you are trying to tackle. Okay, because with your preconditioner, basically you can tackle a lot of parameters better. Let's say so. Maybe you can help me understanding this from the table.
Yes. So this K1, K2, these are the hydraulic conductivities.
Okay.
So basically they are related to diffusion of the fluid. And instead this, what is called the C1, C2, they are, C1, 2 is what regulates the exchange between the networks. So if the exchange between the network is much more important than the diffusion.
Okay, this is a classical, let's say, convection dominated problem.
Yeah, so if that's more important, the exchange between the networks, then those parameters would be much higher than the hydraulic conductivity. But then what happens is that these extra diagonal blocks will become much bigger, much larger than before. And therefore, if we use just a block diagonal preconditioner, it's not going to really work. But the reason why also we wanted to explore the possibility of having, so in this case with the Xc, the exchange coefficient equal to 10 to the power 6, and these K2 coefficients that are like 6 order of magnitude smaller, it's because there is a lot of uncertainty around these coefficients, these exchange coefficients. So our goal was more like, we need a tool, we need a solver that we can feed any parameter and is gonna work, so that we can actually make we can actually make tests or like systematic tests to understand what's the effect of this parameter in the phenomenon that we are want to model. I don't know if this is clear. It's just that sometimes, especially in biology, it's not always possible to measure these things.
Yes,
but then
sure.
numerically, it would be nice to be able to do that. Yeah.
Okay, I see. And okay, so basically the range here with I don't know, with K2 equal 10 is usually for porous medium inside rocks or brain. I think
the more like no, a brain. If we have, let's see if I can.
Now I don't see your screen.
You don't see anything.
No.
Oh. This is very bad.
We can stop once again sharing.
Oh, perfect. Yeah, definitely. So in the, let's see here, for the brain, hydraulic conductivities are really tiny.
Okay. Okay.
Yeah. But what matters numerically is more like the ratio between the different parameters. So if you have a hydraulic conductivity of 10 to the minus 6, but you have a exchange parameter of 10 to the minus 2 or 10 to the power 0, 1, then that's troublesome numerically.
Okay, I see.
Yeah.
Okay, thank you. Thank you, Eleonora. So I don't know if there are questions, but I think not.
I may have
Francesco.
one.
Yes.
I was having another look at the orders of magnitude, and in particular for the K, that as you mentioned in the last answer to Maria's question, they could be kind of small.
Yes.
Okay. And then in maybe it was like 2 or 3 slides, if you can go on. The first slide in which you showed us how the preconditioner works on the simple case in which there was one equation.
You mean something like this?
Yeah, probably 6. Yeah, exactly. So, for instance, if I look at the expression of K tilde and E tilde, I mean, I kind of see that there is a, for instance, in E tilde, there is a 1 over K1 to the power 2.
Yeah.
So if K1 is very small, would this break? And let's say that if K1 is very small, K1 to the power 2 will be even smaller. So would this be an issue? And if it were an issue, would it be possible to just change the names of 1 and 2 and use the other one on the denominator?
Yeah, I think so. All this machinery is based on the fact that this matrix K is actually invertible. So if K1 becomes really small, like close to 0, then this K is not invertible anymore, and we can't really go through this at all. So then I think we need to figure out something else. Yeah, okay. It's a good point. So the hypothesis that we have here is that the matrix K is invertible, so that we can construct this transformation matrix.
Okay, thank you.
Thank you.
Okay, so I think there are no other questions. So I thank again Eleonora for being with us today.
Can you stop my sharing?
Yes, I will. So thank you, Eleonora. And guys, we see each other next year. This was the Christmas AJS. So see you next year. Stay safe and goodbye to everyone. See you.
Yes, thank you. Have a nice Christmas.